In the next property, it is assumed that we have a connected graph with number of vertices at least 2. So what we need to prove? We need to prove that it is a tree if and only if the sum of the degree is equal to 2 multiplied by n minus 1. Since we have if and only if, so this statement is bi-directional. So you have to prove it from left to right as if and then, and you prove it from right to left as if and then. From left to right, you need to prove that if G is a tree, then the sum of the degree is equal to 2 multiplied by n minus 1. And from right to left, what you need to prove? You need to prove that if the sum of the degree of G is equal to 2 multiplied by n minus 1, prove that it is a tree. In both directions, it is assumed that we have a connected graph with n greater than or equal to 2. So first we will prove it from left to right. So the statement will be, for a connected graph G, if it is a tree, then we have the equation I equal to 1 up to n, di is equal to twice n minus 1. We will prove it directly, so by direct proof. Now, since G is a tree with n vertices, then it has n minus 1 edges, and this is one of the properties of the tree. Hence, for the total degree, for the total degrees, and let us write the equation, summation I goes from 1 to n, di is twice number of edges, which is equal to 2 times n minus 1, and this gives us the result of the right hand side of the statement, because this is if and then. So if it is a tree, we have found this equation. Now for part B, so this is part B, we need to prove the statement from right to left. So we say for a connected graph G, if the total degree of the vertices is equal to twice n minus 1, then G is a tree. We will prove this by contradiction. So proof by contradiction. So first we need to write the contradiction statement. We say suppose, and remember that for the contradiction statement, if you have if and then you write P as it is and negation of the conclusion. So suppose we have a connected graph G such that the summation from 1 up to n di is equal to twice n minus 1, and now we write the negation of the conclusion. The conclusion says that it is a tree, then we have to write and G is not a tree. So let us put underline over the given information. The given information that it is connected, and also it is given that the sum of the degree is equal to 2 times n minus 1, and it says that G is not a tree. So we have 3 given information. We would like to use them to find something logically is incorrect. And this is the idea behind a proof by contradiction. So now we are going to write here, since the total degree is equal to n minus 1, then the number of edges is equal to n minus 1. And since G is not a tree, then it has at least one cycle. So this is given to us now, and remember that the sum of the degrees is equal twice number of edges. By matching, we see that this is the number of edges, so we have the number of edges of G is n minus 1. Also, it is mentioned here that G is not a tree, and since it is not a tree and connected, so the only way that makes G is not a tree is that it has one cycle. Now, remove one edge from the cycle to make the graph free of cycles. So now we have a graph G. After we remove one edge, then it is free of cycles because we broke the cycle by removing this edge. Now, the resulting graph has n vertices. Notice that no vertex was removed, and it is a tree. And why it is a tree? Because it is connected and it does not have any cycle, so we will write between a bracket connected and has no cycles. So let us read the statement from the beginning. Now, the resulting graph has n vertices, no vertex was removed, and is a tree connected and has no cycle. Then it has n minus 1 edges. And this is from here. It says n vertices, and since it is a tree, so it has n minus 1 edges. Hence, the total edges of G is equal to, first we have n minus 1 for the resulting subgraph after we broke it from its cycle, plus 1 which is the edge that we have removed from the cycle, and this is equal to n, which is a contradiction. Because G must have n minus 1 edges, which is, see here, at the beginning we said that the number of edges of G is equal to this number, but if it has a cycle, you remove one edge, and then you return that edge back, you will find that it will have n edges, which is a contradiction. The last property in the list is that a tree with more than one vertex has at least 2 leaves, or two vertices of degree 1. We will prove it by contradiction. Proof by contradiction. And the proof by contradiction, we start by writing the negation of the statement by saying suppose not. Now notice the statement looks like if and then. It says if a tree with more than one vertex, if we have a tree that has more than one vertex, then it has at least 2 vertices of degree 1. So the conclusion is at least 2 vertices of degree 1. So the negation statement will be, suppose a tree, and we will give it a label T, with more than one vertex has, and the negation for at least, it will be at most one leaf. And why? Suppose now the number of leaves is L. So we have an inequality L greater than or equal to 2. This represents at least 2. So the number of leaves will be greater than or equal to 2. Now the negation for this one, for this inequality, will be L less than 2. And furthermore, since number is an integer, because it says number of leaves, then this will be L less than or equal to 1. And if the number of leaves less than or equal to 1, we have two cases, either L is 0 or L is equal to 1, because we don't have L negative number, we don't have minus 3 leaves. So either we don't have a leaf or we have exactly one leaf. And according to this, we will divide the problem into two cases. Case 1, if T has no leaves or no leaf, then now what will be the total degree? Then the total degree, which is summation, is greater than the minimum total degree, which is 2n. So this I will put a label. This is minimum total degree. Why this is minimum total degree? Because if we don't have a leaf, and also we don't have a vertex of degree 0, because remember the tree should be connected, so we don't have a vertex of degree 0, so the degree will start from 2. So if all of them are of degree 2, then the total degree will be 2n, and this is the minimum total degree. But we already know that the equation for a tree for the total degree is equal to twice number of edges, and number of edges is n minus 1, which is greater than or equal to n. And this will gives us 2n minus 2 greater than or equal to 2n. Now 2n will go with 2n, so therefore we have minus 2 greater than or equal to 0, and this is a contradiction. Why a contradiction? Because minus 2 is not greater than or equal to 0. For case number 2, if T has exactly one leaf, then the total degree, which is the summation, V belongs to capital letter V, degree of vertex, will be greater than, now we have exactly one leaf, so we will find the minimum total. So here is the minimum total degree. So the minimum will be now one vertex of degree 1, and now the remaining vertices, and how to represent remaining vertices, n minus 1, because if the number of vertices is n, you take out this leaf, so n minus 1. If minimum, all of them are degree 2. So this is the equation we will get, and remember for a tree we have 2n minus 1 greater than or equal to 1 plus 2n minus 2, and this equation will be 2n minus 2 greater than or equal to 2n minus 1. So therefore minus 2 is greater than minus 1, and this is also a contradiction, because minus 2 is not greater than or equal to minus 1. As an exercise, try to find a solution to these three problems. The first one says draw a simple graph that is not a tree with 4 vertices and 3 edges. See if the number of vertices is n, so the number of edges is n minus 1, which is 3. And here we would like to tell you that not every graph, that if the relationship between edges and vertices, that edge is equal to n minus 1, is a tree. except if there is one condition that is violated of the trees. Remember, when a graph is a tree, then you cannot have a drawing for this graph. Is it possible for a tree to have 9 vertices, so n is 9 and e is equal to n minus 1, 2 of which have degree 5. So if you know 2 have degree 5, so how many remaining vertices? You have 7. So what is the minimum degree for the remaining 7 vertices so that you get the minimum total degree? Find it and compare it with the total degree of a tree, and you will see that the answer is no. Last, consider the complete graph. Show that Kn is not a tree whenever n is greater than or equal to 2.